introduce myself. I'm Tom Welton. I'm the Dean of the Faculty of Natural Sciences, and I'm the person this afternoon that you want to hear least from. So I will attempt to be brief. So I'm really just here to say welcome to Imperial College on a lovely drizzly day like we just have, and welcome to the Blackett Colloquium. And really just to say, I now need to hand you on to the people that know what they're talking about in this area, and I'm going to start with the head of our fantastic physics department, Professor Jordan Nash. Over to you, Jordan.
Let me thank you all for coming again. I'm first going to tell you what the running order is going to be today. I'm really going to spend just a few minutes talking about Blackett and what he did, and then I'll introduce the speakers, and they're going to tell you the interesting and fun stuff. And afterwards, a few more words from me, and a lot of chance for you to ask questions, and then we'll wander you upstairs and wine you and dine you a bit. So I hope the day will be interesting for you, and also a chance to socialize a bit and get to talk with us about the science and talk to each other. Let me say, the name of this is the Blackett Colloquium. So what is that? It's an invented name because we thought we want to have an annual event where we invite you to come and hear about our science, and we needed a name for it. And I thought, well, Blackett is the large looming figure in the history of this department, and that's an appropriate name to choose for this annual series and events. So last night I went and read through a few of Blackett's achievements, and I went and read his Nobel Prize citation and his after-dinner banquet speech, and realized what a giant Blackett was, both scientifically and literally. And I'm told by undergraduates who knew him, he was also quite a fearsome personality in going around the department. Some of you can probably confirm that. So what did Blackett, if you look at what Blackett's huge achievement to the field of, my field, so I'm an experimental particle physicist, and he made one of the most fundamental achievements in my field in the 1930s. And what he did was really it seems quite simple and elegant now, but it was something that didn't exist. So the way people looked for elementary particles in those days was either to take a radioactive source or to look at cosmic rays and have a piece of film. So you'd have a piece of film and you'd run a new piece of film through, you'd take an exposure, run another piece of film through, take an exposure, take as many thousands of those as you could, and try to find the interesting ones. Well, that was great, except you'd have thousands of empty photographs, and every once in a while you might have an interesting particle in one of those. Blackett's great idea was to say, we've got these things called Geiger counters now, and I'll take one here, I'll take one there, I'll put a piece of film in the middle, and when a cosmic ray goes through the Geiger counter here and here at the same time, more or less, I mean, it's got travel at the speed of light from here to here, I can make an electronic signal that says, take a picture. And the cloud chambers that he was using still had visible traces of the particles that had come through. And so he was able to do essentially this is what we call trigger nowadays. He was able to make his film, 80% of the exposures he took had something interesting in them. And that revolutionized the ability to study high energy particles. And then he was able to take his big team up on top of mountains in the Alps where the cosmic ray flux was higher and discover all sorts of new particles. So Blackett's big team was him and an Italian guy, which is really much different than the teams we have now studying things at the Large Hadron Collider, which is me and 800 Italian guys and another 2,500 people from all different nationalities. So it's a very different thing, but the problems have grown in complexity enormously. So we do triggering nowadays. I've got engineers and postgraduates and researchers working on triggering for the Large Hadron Collider. The challenge there is you don't just have a flux of a few of these per second. We make 1 billion proton collisions per second at the Large Hadron Collider, and we're not interested in most of them. And so the trick is to make something that does the job of these two simple Geiger counters that works at a rate of about 40 million times a second and can differentiate the sort of 1 out of 1 billion interesting things that are going on per second. So that's the challenge nowadays, and technologically, it's a lot different. So Blackett won the Nobel Prize in 1948, and then we lured him here to Imperial College in 1952. So, I'm going to speak with my dean here about the typical academic package you want to lure somebody with. So Blackett was lured with, we'll give you a building and we'll let you double the size of the academic staff. that worked. So that's probably what we need to do if we want to get Nobel Prize winners to come. That seems to be a winning strategy.
And we're paying £200 a year?
Yeah, exactly. Well, you said, as you say. So just to say, I mean, Blackett actually took a big hand in the overseeing of the design of this building, and he watched it go up. And to just give you an idea about the change in the number of staff, in 1944 there were 17 academics and 1 research assistant here and 16 technicians. By 1960 there were 55 academics, 61 technicians, and 32 research associates. So Blackett had already understood that you can get a lot more research done by hiring research associates. And we've continued that. Now we've only doubled the academic staff. We're 120 academics, but we have 230 research associates at the moment and 100 support staff in the building. So we've continued to grow, but we have squeezed this building to the limit. So we have filled all spaces with research associates, students. We're 1,200 students now, 800 undergraduates and 400 postgraduates. So it's a packed building because everyone wants to come here and do physics. Who can blame them? So Blackett's influence, I'm going to say one more word about Blackett and then we'll let you get started. Blackett also had a huge amount of influence outside of just physics, right? So during the war, Blackett invented this area of research called operations research. So he did something, he went and worked for the Admiralty and studied how you could use science to figure out how to do things like, well, if we have convoys of ships going across the Atlantic and there's submarines attacking them, how can we minimize the damage? So he studied this as essentially a science problem and came up with algorithms to help the operations, the war operations. And this was critically important, right? So Blackett was really part of the political sphere, which was much more, the era of scientists in the 1940s as being influential politically was much greater. And he became Lord Blackett of Chelsea afterwards and still remained quite influential, but he also understood that influence of scientists there was a dark side to it because that influence came as a result of many of the weapons that were developed. And he was quite a serious, deep thinker about the impact of that and the responsibility of scientists in paying attention to that. So that was something where, that era was really something when scientists had much greater say on what's going on. And I think, it's sad to say that scientists these days are not as influential. Science in society, I think, is hugely influential today, but scientists are much less politically influential than they used to be. And I think actually the most influential thing we have as scientists is producing our graduates who go out and spread out far beyond science into a really wide network of influence. And I think it's a change in terms of our ability to influence the direction of governments, but I think it's just a natural progression because I'm not calling up the Prime Minister and saying I've got something new that's going to change the world anymore in quite the same way. It's a slower way but I don't say anything other than science's impact on society is just as great. It's just not as horrific as it was at that era. So I'm going to now introduce you to our young speakers. I purposely chose really young and enthusiastic speakers who know what's going on in the field. They're at the forefront of this and really one of the most exciting topics. They're going to tell you all about it. Again, I'll say just as a particle physicist, I've been studying particles. We think we've got them all ticked off on our chart. And then these guys tell me, oh, we only got 4% of the stuff in the universe, and which makes me feel like there's work still to do. And they're going to tell you how they're going about doing it. So I'll just introduce you to our first speaker. And they'll introduce each other as we go along, and I'll come back and we'll have questions afterwards and a little more discussion. So the first speaker is Roberto Trotta. He's a senior lecturer in our Astrophysics group. He's also a public engagement fellow with the STFC, which is one of our funding agencies, funds him to go out and enthuse people about science. He did a PhD in theoretical cosmology at the University of Geneva, was a fellow of the Royal Astronomical Society at Oxford, and then was appointed to Imperial in 2008. And he's working on advanced statistical methods to combine analysis of cosmological, astrophysical, and particle physics data sets in order to better understand what is the nature of dark matter and dark energy. So Roberto's going to lead us off.
Thank you, Jordan, for your kind introduction, and welcome from myself as well to this Blackett Colloquium. I'm going to start talking about the astrophysical cosmological evidence for dark matter. So if you look up at the night sky, here it is, familiar sight, the moon for scale. What I want you to do, though, is concentrate on this little small square here. It's a tiny patch of the sky. In fact, it's so small that it would fit inside the eye of a needle held at arm's length. And yet, if you observe the sky very carefully, if you observe that patch of the sky with one of the most powerful telescopes we have, the Hubble Space Telescope, this is what we see. That patch of the sky is teeming with galaxies. Each one of those dots in this picture is an entire galaxy. There are 5,500 galaxies in that eye of a needle, and each one of them contains about a few 100 billion stars. And in fact, if we zoom in even further, I can convince you that indeed each one of those dots is a galaxy. So here, a beautiful spiral galaxy. And if you do the maths, it turns out that the visible universe alone contains about 50 to 100 billion galaxies. That's stunning. It's an incredible tapestry in terms of the universe we live in. And yet, as Jordan was hinting, one of the most incredible discoveries of modern cosmology is that, and I hate to be the one that's breaking you the news, this is only a tiny little bit of everything there is. 96% of the universe is missing. It does not show up in that picture. And the big slice of that 96% is what we are concerned with here today, dark matter. And so if we look even further afield to the furthest reaches of the visible universe, more about this map in a second, we realize that actually there is a dark side to the universe. And that is one of the most important, most fundamental mysteries in the entirety of physics, perhaps in the whole of science. So if you look more carefully at the composition of our universe, this is the cosmic recipe. Only this tiny little sliver here is showing up in the Hubble Space Telescope picture that we saw. About 4% in total in the universe is made of normal matter, the kind of matter that you and I are made of, although most of it is non-luminous. And it wouldn't show up in the picture, like interstellar intergalactic gas and neutrinos, etc. 23%, about a quarter, is dark matter, and 73%, perhaps even more surprising and even more disturbing, dark energy. We won't have time today to look into dark energy, although it's another fascinating topic. But if we could at least crack this bit here, we would already have made big progress in understanding what the universe is truly made of. To put it simply, and what I did in order to put it simply is I recently wrote a short book called The Edge of the Sky, which is unlike any other science book you might have seen or read before, because it only uses the most common 1,000 words in English to describe the entirety of the universe. Now, universe is not one of them, so I can't use universe in the book, so that's why the book is called The Edge of the Sky, All You Need to Know About the All There Is. And so how do you describe the dark matter problem in very simple terms that everybody would understand? It seems crazy that student people, that's us, should think that there is a lot more stuff that you can't see than stuff that you can see. Still, they do. In fact, they believe that there is about 5 times more dark matter than normal matter. Gladly for me, dark matter, both these words are in the 1,000 most common words in English, so that's good. If you look around us with a far-seer, you will realize that the white road is made of many, many stars. There are about stars in the white road for each person on our home world. And if you use a big seer, you will find there are as many other star crowds in the sky as there are stars in the white road. And yet, all of this is just a tiny bit of everything there is. And then the book goes on and explains what we understand about dark matter, and crucially, what we still don't understand. This is what we're going to tell you today. Now, this is a very thin little book, and it explains everything there is to know about the universe in only 73 pages. And it's a beautiful object, and with Christmas coming up, and that uncle that you never know what to give to, it's very reasonably priced, etc. So if there is dark matter out there, what is the evidence? After all, we are scientists. We need to have observational, experimental evidence for these extraordinary claims. In fact, the problem of dark matter goes back 80 years. And one of the first people, student people, perhaps, if you want to call them like that, to realize that there was something strange going on with gravity was this chap here, Fritz Zwicky, a Swiss-American astronomer who was not particularly known for his good manners. But what he did discover, paraphrasing what he found, was that if you looked at the rotation of galaxies, here is a beautiful example of a spiral galaxy, indeed our nearest neighbor, the Andromeda Galaxy, a mere 2.3 million light years away from us, in our cosmic neighborhood, so to speak. If you look at how fast those galaxies spin around their axis as a function of the distance from the center, well, you realize that a simple calculation will tell you that a star, say here, has to be subject to the gravitational pull of the matter inside the galaxy. And at the same time, if it rotates around the center of the galaxy, there's a centrifugal force that pulls the star out. And the two have to be balanced for the star to be kept part of the galaxy. And so because you realize that most of the visible matter in the galaxy is concentrated at the center, the calculation shows, under Newtonian but also under Einsteinian gravity, that you expect the rotational velocity of these stars to decrease as a function of the distance from the center. But what Zwicky was among the first to realize, and countless observations have confirmed ever since, is that actually the rotational velocity of stars is rather constant with distance. It does not go down as predicted by Newton or Einstein for that matter on these scales. And so to this puzzle of the constant rotational speed of galaxies, there are only two possible solutions, really. One, Newtonian gravity and Einstein gravity are wrong, and so we don't understand gravity on galactic scales. That's very difficult to accept because Einstein certainly has been proven right with very high precision. Or there is more than meets the eye. There is more invisible mass out there that's generating the extra gravity that's keeping those stars as a part of those galaxies. And that was the first notion of dark matter. Since then, of course, we've moved on in our understanding of gravity and space-time. Space-time, this idea introduced by Einstein in 1916 in his theory of general relativity, and 1915, I should say, because this year is the 100th anniversary of general relativity. At the end of November, we celebrate 100 years of general relativity. And the key insight of Einstein was that space and time are not two separate entities. They are actually merged in one single continuum, the space-time continuum, that has got one key property. It's malleable, it's dynamic, and it responds to the presence of mass. And so if you have a massive body in space-time, the shape of space-time gets bent by the mass of that body, and vice versa, masses, particles, even photons, particles of light, respond to the shape of the space-time continuum, and their trajectory is altered accordingly. And so one of the key predictions of general relativity is that if you have a massive body such as the sun, and you have a beam of light coming towards us, just past the rim of the sun, the change in the shape of the space-time brought about by the mass of the sun will deflect the trajectory of light in such a way that the apparent position of the star and the true position of the star will be separated by a certain angle, an angle that Einstein was able to compute very accurately, and that an expedition in 1992 expeditions sent out by the Royal Astronomical Society, one of them was led by the famous astronomer Eddington. Two expeditions confirmed in 1919, which was the moment that made Einstein the scientific superstar that he were to become. And so this deflection angle has been measured experimentally, so we know that Einstein gravity works. We know that general relativity is a good description of space-time, and now I'm going to apply this very same principle to cosmological scales, scales which are vastly bigger than the scale of the solar system. And that's, I believe, as close as you can get to actually being able to visualize dark matter with your own eyes. There's another beautiful picture taken by the Hubble Space Telescope. I hope you can see that there are plenty of little arclets here in this picture. There's one here, there's another one there, there's one here, one there. What we are seeing in these arclets is nothing else but the image of background very distant galaxies whose light has been traversing the universe and has been deflected, distorted by the changed shape of space-time brought about by the intervening mass, the mass of this galaxy cluster here, which is the orangey galaxies that you see in the forefront. And now, because we know what gravity does and how gravity works, we can work out how much mass you need to make enough bending, to bend space-time enough to generate those images. Then you can compare with the actual visible mass, which is the one that you see in using visible and other type of light, and the two do not match up. You need extra mass in that cluster to explain the bending of gravity as observed in this picture. Another strong evidence for dark matter. There's many more examples. I do want to give you one of the pillars of modern cosmology. This picture here, what you're seeing here is a picture of the baby universe. That's Real data obtained by the Planck satellite, which has heavy Imperial involvement. Some of my colleagues in the Astro group have been instrumental in generating this map and understanding what it means. And what you're seeing here are red dots, slightly higher temperature places in the universe, and blue dots, slightly cooler places in the universe, as it was 380,000 years after the Big Bang. This light has been traveling 13.7 billion years across the universe, and it comes from a period of time in the history of the universe where galaxies did not exist, stars did not exist, simply because all there was in the universe was light, helium, hydrogen, dark matter, a little bit of dark energy, but nothing much to speak about, and neutrinos. So that's a picture of the baby universe that we have come to understand in great statistical detail. Indeed, if you analyze those data statistically, this is what you get. The details of this plot do not matter, really. What I want you to notice is one stunning thing. The data are the blue dots. You can see that they are arranged in a very distinctive shape, which is reminiscent, perhaps, of a sound wave. And that's not random. It's a sound wave because, indeed, we are seeing sound waves in the early universe, sound waves of a wavelength of 450 million light years. But what is incredible is this red line. This is our best fit cosmological model. That's the best description we have of the universe, which is based on three pillars: general relativity, inflation, very fast expansion of the universe very early on, and the existence of dark matter, dark energy. Without dark matter, without dark energy, you would not be able to get this incredible fit. And look at the precision of this fit. The red line goes bang through all the dots. And this is an amazing feat of modern cosmology, but one that leaves us in troubles, because these data are telling us we need dark matter. 23% of the universe is made of dark matter, and yet we don't know what it is. So I hope I've convinced you that there is something out there, and if that something is a new type of particle, more about which we'll hear from our next speaker, we should be able to detect it in different ways than just by its gravitational effect. It should have particle physics properties that we can investigate. In particular, in certain models called supersymmetric models, the dark matter particle can self-annihilate. And in the process, it will emit, among other things, high-energy light, a type of light called gamma rays. And so if we look at the sky in gamma rays, perhaps we can catch the glimpse of the annihilation of dark matter particles, which, according to our theoretical model, are all around us. There are about 50 million dark matter particles going through your hand every second in this very room. So there's plenty of dark matter out there. The question is, how do we catch it? Here's a picture of the gamma ray sky taken by the Fermi satellite. And you can see there is plenty of gamma rays in the sky, but most of them come from astrophysics, nothing to do with dark matter, except if we zoom here towards the galactic center, that's where we expect most of the galactic dark matter to be concentrated. What you see, once you have cleaned out all of the astrophysical emission of gamma rays, at least the one that we can account for, what people have been seeing in the past few years is a strange blob right at the galactic center, one that shows an excess of gamma rays above what you expect from astrophysics alone. And if you compare that excess with what a dark matter signal would look like, the two look pretty much the same. So is this perhaps the very first signal, dark matter signal, that is not gravitational in origin? Are we seeing dark matter in the sky? The way to tell is by combining all of these different lines of evidence. This is what I do in my research. I put together cosmological data, direct detection data, experiments, laboratory experiments of the kind that Henrique is going to tell you more about. Large Hadron Collider data, production of dark matter and other beyond the standard model particles. Sarah's going to talk to you about this in a moment. And astrophysical probes of dark matter in one unified framework that tries to attack the dark matter problem from all possible angles. Because combined, these four probes are so much better than each one taken in isolation. So I want to finish by showing you the power and indeed the need for cross-disciplinarity in attacking the dark matter problem. So this is a rather busy plot, so let me just take a minute to explain. On this axis, the mass of dark matter. It's unknown, of course. That's one of the things that we are trying to find out. Units here are such that one is about the same mass as a proton. On this axis is a measure of the interaction strength, or the probability of interaction of dark matter. We call it the cross-section. To give you a feeling for those numbers, I put them in units that perhaps, just perhaps, can make sense. Here's a ping pong ball. And the cross-section of the ping pong ball is just its area. So I want you to picture the ratio of the cross-section of the ping pong ball to the sun. And I'm telling you that the ratio between the cross-section of the sun and that of the ping pong ball is the same pretty much as the ping pong ball to the cross-section for a nucleus. That's easy. The nucleus is easy. Indeed, there is a reason why we call the typical cross-section of a nucleus a barn, more about which later ask me if you want to know what the story of it is. But now I want you to take another jump down, again by the same difference in orders of magnitude from the nucleus, another jump down, and that's where the dark matter lives. That's how difficult this particle is to catch, and this is 1 in this plot. Okay? This is tiny. That's how hard the job of Henrique and his colleagues is to catch this particle in the lab. And so this is think of this as the dark matter continent. Those dots represent possible dark matter values for the dark matter mass and its cross-section. They're all over the place. We don't know hardly anything about this particle if we only use cosmology to constrain its properties. But then we start combining things together. Let's add the direct detection constraints, laboratory measurements that have failed so far to come up with dark matter. This part here is sliced off the top because we haven't seen it yet in the lab, so we can remove these possibilities. Let's add the searches for dark matter that have been made at the Large Hadron Collider to date, which have not come up with dark matter yet, and only the blue points remain. And now let's add in the gamma ray excess from the galactic center, and this is what happens. Now we have zoomed in to 2 islands of very high probability where the dark matter particle could be, and I can tell you more. We can actually put a target on the dark matter particle. This is our best guess for where the dark matter particle lives in this realm of possibilities according to a specific theoretical model. And this line is where Henrique and his colleagues are going to get to experimentally by 2020. And so if dark matter is here, they will find it. And so to conclude, I think in the next 5 to 10 years, we'll see Imperial be part of the story of dark matter for sure because of all the reasons that I told you. And perhaps we'll be even part of the history of dark matter by actually being the first ones to find it. Thank you. I'd like to introduce our next speaker. Sarah Malik is a Royal Society Fellow with the High Energy Physics Group at Imperial. After gaining a PhD in particle physics from UCL, she moved to Rockefeller University as a postdoctoral researcher before joining Imperial in 2014. Sarah works on searches for dark matter particles at the LHC and developing the interface between theory and experiment for dark matter. Sarah, over to you.
Okay, great. Thank you, Roberto, for the introduction. So as you heard from Roberto, dark matter is everywhere. It makes up such a large fraction of our universe, and yet we know so little about it that we take a multifaceted approach to try to figure out what the nature of dark matter is. And one such approach is to try to see if we can create dark matter particles in the lab and then study them and see how they interact with us or normal matter. And so this is what my talk will be about today. How do we search for dark matter at colliders? So as I said, we really don't have much knowledge about what dark matter is. And so there are a plethora of different ideas or models that we proposed to determine what the nature of this particle, whether it's a particle, and if so, what type of particle it is. And one of the most popular of these goes by the acronym of WIMPs. So this stands for weakly interacting massive particles. So the idea is that these WIMP particles were created in the early universe together with everything else. So the early universe was a very high energy place. So particles of matter and antimatter were continually being produced, and then they were coming together, annihilating, and they'd disappear in the puff of energy. And so these dark matter particles, as the universe expanded, it cooled. And as it cooled, there wasn't enough energy available to continually produce these particle-antiparticle pairs. So we think the same happened with dark matter, that at some point there just wasn't enough energy to continually produce these WIMP particles. Now, the reason why this particular idea is popular is because there's a remarkable coincidence, which is that particle physics, which studies the fundamental constituents of matter, and cosmology, which studies the large-scale structure of the universe, the order of the scale of the universe, both of them point to the same scale for what dark matter should be. And this is called the WIMP miracle. And this is why this actually lent the fact that these two very different disciplines looking at extremely different scales point to the same place for what dark matter should be. This is called the WIMP miracle. And this actually lent a lot of credibility to this particular idea for what dark matter might be, as opposed to the other ones that we have out there. OK, so we have our hypothesis for what it might be. So how do we go about trying to discover it? So I mentioned that these WIMP particles were created in the early universe as a result of high-energy particle reactions. So we ask ourselves, can we recreate the conditions that were prevalent shortly after the Big Bang and that are necessary to produce these dark matter particles in the lab? Because if we can produce them in our lab, then we can study them, and we can study how they interact with us. So what do you do if you want to recreate the conditions that were prevalent shortly after the Big Bang? You build a huge collider. And this is where the Large Hadron Collider comes in. So this is the world's, I'm sure you've all heard of it, so this is the world's highest energy particle accelerator. It's one of the largest and most complex scientific instruments ever to be built. It's truly an engineering marvel. So it's located on the border between France and Switzerland, about 100 meters or so beneath the ground. And it consists of a 27-kilometer ring in which we accelerate beams of protons to almost the speed of light, and then we make them collide. And we see what comes out of that collision. When they collide, it creates a tremendous amount of energy. And that energy is then used to create new particles. So in much the same way that these high-energy particle reactions created dark matter particles in the early universe. We've already had success with this. So in July 2012, we announced that we discovered the Higgs boson, which is a fundamental missing piece in our particle physics model. And we hope to have similar success with the dark matter puzzle. I just want to give you an idea of what a huge scientific endeavor like this is really. It's a global venture. So the lab that hosts the Large Hadron Collider, or CERN, there's 10,000 scientists, technicians, and engineers from all around the world, representing over 600 universities and over 100 nationalities that actually work here to put all of this together. So it's not just a feat of engineering and probing the frontiers of science, but it's a spectacular display of diversity and international cooperation. In our office the other day at Imperial, so there's 5 of us in our office, and so we were counting how many nationalities or ethnicities we represent. So it turns out all 5 of us actually represented a different ethnicity or nationality. There was English, there was German, American, Pakistani, and Algerian. And we all work on this, on the Hadron Collider. OK, so to give you some more fun facts and figures about this. So it's been dubbed the fastest racetrack on the planet because we're accelerating these protons to very, very close to the speed of light. So we're circulating them around this ring. And in order to bend them around this ring, you need very strong magnetic fields. And in order to create these magnetic fields, we actually need superconducting magnets, which have to be cooled down to temperatures of the order of minus 271 degrees Celsius, which means that the LHC operates at a temperature that's colder than outer space. Also, when they're going around these beam pipes, you don't want them to collide with anything else, like other gas molecules in the beam pipes. And so these beam pipes are actually kept at an ultra-high vacuum, which means that there's actually 10 times more atmosphere on the moon than inside the LHC. So it's the emptiest vacuum, apparently, in the solar system. The point at which these proton beams come together and collide, so it generates temperatures that are 1 billion times hotter than the sun. So it's one of the hottest spots in the galaxy. So we do this at 4 different points on this ring. So we bring these proton beams together, we squeeze them and focus them into a tiny point such that they collide. And we do this at 4 different points. And at these 4 points, we've placed gigantic detectors. So these are also some of the biggest and most complex detectors that have ever been built. They act like giant digital cameras that are very fast. They're capable of taking more than 40 million snapshots of these collisions per second. And they're also very precise. So we can study these particles with incredible accuracy. And this is just a picture of 2 of the experiments that we work on here at Imperial. OK, so if we were able to produce these dark matter particles in our collider, how do we know that they were produced? We know that dark matter doesn't really interact with anything. We know that it's neutral in charge. It doesn't have electric charge, so it's neutral. We know that it's very weakly interacting. And it leaves, therefore, no visible trace in our detectors. So how do we know that it was produced? So back in 1930, Wolfgang Pauli was looking at the conservation of momentum. He was looking at how much momentum was produced before and after the decay of a neutron into a proton and electron. And he was coming up a little short, i.e. momentum was not being conserved in this decay. And so he concluded that there was another tiny undetectable particle that was also being produced in this decay, but that was not being detected, and it was taking away some of the momentum from that system. And that particle later turned out to be the neutrino. So he basically postulated the existence of the neutrino. In much the same way, because dark matter is like the neutrino, it's neutral and it's weakly interacting, we'll try to infer its presence by applying momentum conservation and seeing how much momentum imbalance there is in a collision. So this is a 3D snapshot of a real event that was recorded by the CMS detector. So you can see here that this Lego-like block here is the energy deposit from an object. And you can see on the other side, it's not balanced in momentum by anything on the other side. And so there's an imbalance in momentum. The momentum is not being conserved in this event. So we postulate that there must be that in this collision, we produced some particle that was neutral and that was weakly interacting, and that actually carried away some of the momentum in this collision. Now, most likely in this particular event, it was just a neutrino. We're not really interested in those ones. But hopefully, at some point down the line, we will observe a lot of events where the particle carrying away this momentum will actually be a dark matter particle. OK. So the Hadron Collider has just started up again after a 2-year shutdown, where we upgraded a lot of things such that we can collide these proton beams at much higher energies than previously probed. So we're really at the energy frontier now with much higher energy. And this phase of operations is called Run 2. So whereas Run 1, we made headlines by discovering the Higgs boson, really hope that in Run 2, we'll be able to discover something that will tell us what dark matter really is. Okay, thank you. Okay, so our next speaker is Henrique. So Henrique is a reader in the high energy physics group. He leads the Imperial team on the direct search for dark matter using the LUX experiment, and he's also the UK principal investigator for the next generation LUX-ZEPLIN experiment. Previously, he was the last spokesperson for the Zeppelin 3 experiment at the Booby mine, which was built at Imperial. And he's going to tell us how we might go about detecting galactic dark matter in the lab.
Thank you, Sarah. Right, good afternoon, everyone. So my name is Henrique Araujo. I'm an experimental physicist in the high energy physics group here. And I'm trying to detect the dark matter that is in our galaxy, that was produced right after the Big Bang. So in contrast to Sarah, that is working at the LHC to try to produce new particles of dark matter, we are trying to detect directly the dark matter in our galaxy that was produced just after the Big Bang. We don't quite do that in the gutter. We actually do that well below the gutter in underground laboratories, and I'll mention a little bit about those. But before that, I want to bring you back down to Earth, just to show you a nice picture. This is a simulation of what the dark matter in our galaxy may look like. And you see immediately and straight away that this does not look like what we normally call our Milky Way. And the reason you can maybe figure out, there is a length scale here which is 8 kiloparsec, and what we call the Milky Way is typically 30 to 40 kiloparsec. So it's more like this. So this is what we think the dark matter halo in our galaxy looks like. It's a huge object. It's quite kind of lumpy. It's three-dimensional. It does not look at all like the disk of stars and gas that we usually call the Milky Way. So if we zoom in, you can see that there is still plenty of dark matter where we are. So the yellow shading shows you the concentration of these particles. And we are more or less there. And so there's plenty of normal matter where we are, and we are evidence for it. But clearly, there is also a lot of dark matter that probably is going through us. And in fact, we think it is. So there is nothing special about the Milky Way as a galaxy. It's cloaked in a halo of dark matter like most galaxies, or like all galaxies. And the total fraction of normal matter is very small. And we have to try to figure out, what does our dark matter look like? How much of it there is and how fast it's moving? We think that there's about one large particle per pint of volume. So what is one large particle? We don't know what a particle is, so how do we know the mass? We don't know the mass. So if you assume that the mass is more or less the mass of a Higgs boson, and you could be wrong by 100 times either way, it doesn't matter, but we have some evidence that it might be reasonably of that order. So that's as large as about 100 protons put together, or a large atom. Then if you assume that the particle is of that order, there should be about 1 per pint of volume where we are on Earth. We also know from dynamics and from astrophysics, and from thermodynamics, in fact, how fast these particles are moving. And they are not moving very fast at all. They are moving at a few hundred kilometers per second, which for a particle is actually not a lot. So that's why we call this cold dark matter, because these particles are going through in all directions and are going through us all the time. And you can try to calculate how many particles are going through you. And if you put your fingernail like that, it should be about 100,000 or thereabouts. That's not a lot. There are 65 billion solar neutrinos going through the same fingernail right now, and we know that for a fact, and we can measure neutrinos. And so I also like this comparison because here again, in neutrinos and solar neutrinos in particular, there's a very elusive particle that also interacts via the weak nuclear force or the weak interaction. And it took a really long time to detect neutrinos after they were first postulated, but we got there. It took 30, 40 years. It took 50 years for the Higgs boson when we got there in the end. So we've only been looking for WIMPs for about 30 years, so we still have some work to do. And if they interact, however weakly, however infrequently, how can we detect them? Well, the simplest interaction you can postulate is a simple elastic scatter, an elastic collision between a dark matter particle colliding with the nucleus of an ordinary atom and then going about its way. So for example, if you have a matrix of or a crystal or some heavy liquid, for example, full of normal atoms, we expect that very occasionally a WIMP might come through and knock an atom, knock a nucleus, make that nucleus recoil a little bit, and what we're trying to do is to detect the recoil of that nucleus. Why is that difficult? Because these particles are actually not moving very quickly. And the recoil of that nucleus might be only a few micrometers long. And so we have to detect micrometers in some detector, some radiation detector. We also have to determine that what moved was a nucleus and not one of the atomic electrons, because most particles that hit atoms hit the atomic electrons, and that's what happens most of the time. So this is an incredibly difficult experimental challenge, because you can do rare event searches very successfully, as neutrino physics attests to. We can also detect low energies very well if you have a small detector, because then you can pull out the signature of that interaction very effectively. What is really hard is to do both things at the same time, to do a rare event search for very low energies at the same time. So you need a very special radiation detector that scales up gracefully, so the bigger you make it, it doesn't degrade your ability to pull out very small energy deposits, and you need to do that in a very quiet place. So how do you go about detecting a WIMP? So take a 1 kilogram detector that one might build in the lab and make it sensitive to very low energies. These are the kind of rates that we are trying to detect. So to put us on that plot that Roberto showed you in the first, in his presentation, we need to detect these kind of rates. And we are looking for a WIMP that comes through and it scatters from an atom of some sort, from a nucleus, makes the nucleus recoil a tiny bit and then goes about its way. If you've ever seen even a small Geiger counter or any radiation detector that you switch on in the lab, if you have a reasonably large detector, this is what happens. Everything, all hell breaks loose. you do not measure this. You measure something which is much more like this. So you measure many counts per second, even hundreds of counts per second, even from a small detector. And that is because there is radioactivity in everything around us. Even the human body is emitting about 10,000 gamma rays per second. There are cosmic rays going through us and so on. And so clearly we cannot find this kind of number over that kind of number very easily. We have to make this better. So this is the kind of needle in a haystack kind of problem. There's an additional problem that neutrons are actually would be a good WIMP candidate if we didn't know any better. And that is because they are also reasonably heavy, and they have no charge, and they can also create nuclear recoils as they scatter from nuclei. So we have to be particularly careful with neutrons and making sure that there are no neutrons flying around in our geometry, in our detectors. So what we have to do is, the first thing is we go underground. We have to move into deep underground laboratories to do our searches. And you need at least 1 kilometer of rock between us and the cosmic rays, ideally 1.5 kilometers. We have to select the materials that you use to build your experiment from. And that is really why our experiments take so long to build, because we have to screen for radioactivity hundreds of materials and devices and their subcomponents and so on. And we have to select for radioactivity for absolutely everything we use to build our detectors. And then you have to shield against the radioactivity that is naturally present in your laboratory, in the walls, in the rock, and so on. And you shield in a different way for gamma rays and for neutrons. You ideally would like to know if there are neutrons flying around in your detector. You'd like to know that they are there. And so what we tend to do is to instrument one of these shields to make sure that we know when a neutron is around. And ideally, we want also to discriminate nuclear recoils, which could be signal, so the recoil of the nucleus of the atom, from the recoil of just an atomic electron, which is not a signal in its background. So this is the technology that can do all of these things. So that's called two-phase xenon technology. And it's a technology that was actually pioneered here at Imperial College about a decade or a decade and a half ago. And it's the most successful dark matter search technology and has been for a number of years. So this is what we are working on here. It's called two-phase xenon because xenon is quite a special noble gas, and it's a gas at room temperature. We need to cool this to minus 100 degrees, and then it's a liquid. It's a beautiful, transparent liquid that has some amazing properties. And we call it two-phase xenon because we use essentially a bucket, a high reflectance bucket full of liquid, but we keep a little bit of gas on top that has a very specific function. So these are the two phases, the liquid and gas phase. When a particle comes through and interacts with an atom of xenon, either an atomic electron or the nucleus, the first thing that happens is a prompt signal. So it's a prompt flash of light, a very tiny and brief flash of light that we call scintillation. And that light that is shown here is detected by two arrays of photon detectors. There's one array in the gas phase looking down and one array in the liquid phase looking up. We call that the S1 signal. I'll show you some examples later. The second thing that happens is when the particle interacts with the xenon, the atoms nearby sort of shake about a little bit and they lose some electrons, and we try to collect these electrons too. And we collect them with an electric field and we move them up to the surface of the liquid. And when they reach the surface, they get emitted into the gas, and then you have a second flash of light. And that is a delayed signal that we call the S2. So as the particle comes through, this is what you'd see in an oscilloscope. You see a tiny flash of light called S1 light, and then the electrons drift to the surface of the liquid, and when they reach, they get emitted, and you see a second flash of light. These two flashes of light happen for every single particle and tell us two things. Where the interaction was in 3 dimensions. So we can tell within a millimeter or so in X, Y, and Z where that interaction happened, and that's extremely important for our data analysis. And they tell us what kind of recoil actually happened at the interaction. Was it a nucleus recoiling, or was it an electron recoiling? The ratio of these two areas tells you that. So this is the LUX experiment that we are working on and are running right now. LUX stands for Large Underground Xenon Experiment. And you can see here, so there's a high reflectance cage which has 250 kilograms of ultra-pure liquid xenon, all at low temperature, and 2 arrays of photomultiplier tubes. These are just the photon detectors. And if you look up, you see this picture, that's one of the arrays of photomultipliers. There's a tiny signal here, which is really the smallest signal that LUX can detect, which has 2 detected photons for S1 and about 20 detected electrons for S2. And we know this is not a WIMP because the ratio of 20 to 2 tells us this is probably a gamma ray and not a nuclear recoil. So this has been deployed in 2012 in this place. The SANFORD Underground Research Facility, which is where we operate LUX. It's the former Homestake mine. The Homestake mine is one of the original gold rush mines in the US, going back 150 years or so. This is the beautiful hills of, the Black Hills of South Dakota, and it's about an hour away from this gentleman, Mount Rushmore, which is also around there. And what you can see here, you can see the head frame of the Yates shaft, and we go down here. This is our surface administration building, and we go about 1.5 kilometers underground to a cavern where the cosmic ray flux is about 10 million times lower than it is on the surface of the Earth. And really, that is the reason why we work there. We get rid of pretty much all the cosmic rays. This is the town of Lead in South Dakota. It's a very small place, only 3,000 people or so. There's a big hole called the Open Cut, which is where the mine actually started. So this is a feature of Lead. And this is a picture of man and beast. So it tells you how hard it was to work in those mines for all those years. So the situation is much improved because we have PhD students now that do a lot of the work. So if you go into our nice laboratory called the Davis campus, this is what you see. There's an 8-meter diameter water tank, which is what we shield LUX with, and we also read out any signals from that water. And inside that water tank, this is what happens, and that's the LUX titanium low background cryostat, so the experiment is there. And this is a person here for scale. So normally this is completely full of water as we are operating. This is where we are. So you've seen this plot before. This is the mass of the hypothetical mass of the WIMP, and something reasonable is between 1 proton and 10,000 protons, and we don't know what it is, so we have to calculate our results for all the possible masses. And this is how frequent or infrequent the interaction is, like Roberto explained to you. So rarer interactions, we are down. This is the LUX result in green, which is the best in the world, and everything above this is excluded. So as we build more and more sensitive experiments and keep finding zero, we can exclude everything above this, and you can see several features from this plot. So you can see the shaded regions here that are regions where the theorists say we are more likely to find this dark matter. So we have some way to go. There were many more of these shaded regions up here that the experiments have excluded over the last 30 years. But we still have some way to go. And the other thing you can see is that this is a crowded plot, and it would be much more crowded if we had shown all the experiments. And this is a really competitive field because everybody wants to be the first to detect this dark matter. So where are we going after LUX? So LUX is running. The next generation detector is called LZ for LUX-ZEPLIN. So ZEPLIN was actually the UK-led program that we have been working on for almost 30 years. Well, started about 25 years ago or so. And that consisted of the Zeppelin 1 and 2 experiments. Zeppelin 2 was actually the first detector of this kind to work for dark matter. And then we built Zeppelin 3, actually in this very department. So we built Zeppelin 3 here, operated at the Boldy mine in North Yorkshire until about 2012. And then we joined our US colleagues in LUX, which is a much bigger project, and now the two collaborations came together for LZ. So this is the LZ collaboration. These endeavors are getting bigger and bigger. We're not quite at the CERN stage, but we are now working in teams of about 200 people from 30 institutes in our case, in the US, the UK, Portugal, Russia, China. There's a number of institutes in red, which are the UK ones, and we actually lead the UK contribution to LZ. This is what it will look like. It will operate exactly where LUX is at the moment. So we will decommission LUX next year, and we will start building LZ there. And this is the water tank that you've already seen, and we are going to use pretty much the same infrastructure. It's extremely expensive to do infrastructure on the ground, as you can imagine. So we're going to use the same water tank, but what we're going to do is to install a much, much larger detector that will have about 10 tons of liquid xenon rather than 250. 7 tons is the active liquid xenon that produces these two flashes of light. And we're going to surround it with 25 tons of an additional detector that will tag neutrons and other background particles. So we want to make sure that not only we detect a signal from WIMPs, but also we can rule out all the backgrounds. And we are about here. So we've had 3 years of design. We haven't quite completed all the design, but we already started construction of some of the subsystems. And it'll take us 3 or 4 years to build this and to screen all the materials that are going to go into this construction and so on. And then we start running in 2019. So by way of conclusion, I think that we really have a good chance of fixing this dark matter problem in the next decade. I think it's clear to me that because now we have this overlap in sensitivity between the direct search experiments like these and the LHC run-2, the indirect experiments that look up into the skies that Roberto mentioned, and we're all now sort of converging on what this dark matter might be, and these next generation experiments have the sensitivity to pin it down if it's indeed there. And also I will say that Imperial really has leading teams in all of these areas, so we are a very special place for that reason. So I just want you to leave you with some signals from LUX. Hopefully they are here. They're not here, they are here. So this is an app that we have that connects to the underground laboratory, and hopefully LUX is still running. It was this morning. So what we do is we take data from underground and okay. And then we package that just for display purposes. The data is much more complex than this. Okay, I think it's going to start. And then we actually send this data from and distribute this data. What you'll see here is how the detector works with real signals, and the timestamp that should appear here is only a few minutes delayed from the data we're actually collecting underground. So that should be about 4 or 5 minutes. That's right. So you can see the small S1 signals and the larger S2 signals here separated in time, and the top array and the bottom array of photomultipliers. And there's an interaction, and then something that you can't see because it's a little bit faint is there's a representation of an election cloud moving up. And these are actually signals coming from the LUX experiment. So we are doing now a 1-year-long run, and we're more than halfway through it. And these are actually signals that could contain the dark matter that we're looking for, but we won't know for a while yet. Thank you.
So great talks, everyone. I want to invite our speakers up, and now you can grill them. So it's your chance to ask questions. So don't be shy. They're all very excited to answer your questions, and I'm sure you have lots of them. Yes. Siba, just behind you.
Thank you for. Thank you for 3 very interesting talks. In the first talk, there was a slide about dark matter particles annihilating each other and then releasing high energy photons. What are the theories around how that mechanism might work? Are there any theories behind that at the moment?
Yes, the details of how exactly that annihilation proceeds will depend on the properties of dark matter. And in fact, we try to reverse engineer that in order to learn about the particle physics properties of dark matter. So dark matter will not give you photons directly. It's possible, but it's a very rare process. And so it will give out other type of particles, which will eventually give out photons in the process. And it's a long chain of reactions, nuclear reactions, that eventually give out light. If you get these gamma rays at the end, and you can clean out the astrophysical background, which is massive. There's so much more astrophysics going on at the center of the galaxy. That's a very busy place. There is a population of thousands of millisecond pulsars. There's a supermassive black hole. There's hot gas. So all sorts of other things that can and will give out gamma rays. But if you can isolate the gamma rays that are potentially from dark matter, then you can reverse engineer statistically this chain of event and reconstruct the dark matter properties that will give you this kind of spectrum in terms of the energy distribution of the gamma rays that you've observed. But the details depend very much on the particle physics model. And
the 3 talks that we've heard are all assuming that we're actually looking for a particle. Has the possibility of more prosaic substances being ruled out, such as dark stars, black holes, molecular hydrogen, and you name it? I mean, there's many other possible sources other than particles.
Maybe I'll just give you a astrophysics view of that. there's one line of evidence that's very strong that I haven't had the time to present, which is we can measure the ratio of hydrogen to helium from the primordial universe, the ratio of helium that's cooked in the Big Bang itself, the first 3 minutes. And that ratio is very sensitive to the amount of protons and neutrons that you have in the universe. So by measuring the primordial ratio of helium to hydrogen cooked in the primordial furnace, we can work out how many baryons, how many neutrons and protons there are in the universe, and that number is 5%. Agreement with the cosmic microwave background oscillations that I've shown, which also give you a different, experimentally completely different handle on the very same number. So that number is little less than 5%, and therefore, if there is 23% matter, the other 20% cannot be of the same kind of standard model particles that we are made of. That's one of the astrophysical views, but maybe there's other. Right,
no, I think the cosmic microwave background is a great example. The universe was very young, and it was very simple. And at that time, we had hydrogen atoms, we had electrons and protons, and we had neutrinos, but not much more. And there were no stars, and there were no black holes. The concentration of dark matter we arrive at is pretty much the same as from cosmological studies after the cosmic microwave background and from astrophysics now. So we have the same answer from a totally different type of experiment that asks what exists just after the Big Bang, before the universe is complicated, and we're getting the same answer. And it's very difficult to come up with explanations that involve gravity so early in the universe. And so that has pushed us to think that particles is really the only sensible explanation at this point. I mean, it's not we are not 100% sure, but we are pretty sure.
Another possibility is perhaps, I know there's been some interesting work on what they call brains. I mean, using the language of string theory, other universes overlapping our own. And there are suggestions that might be affecting the redshift and causing some of the gaps in the pattern of galaxies and so on that we see, which shouldn't be consistent with the cosmological origin. Is there any possibility that the matter which is causing these the effects of dark matter is actually matter in another brain and is bending space-time in our brain rather than actually being particles in this one? Is that kind of idea being looked at all, or is it just absurd?
You take that one.
Thank you. Okay. Now, I want to make one. That's a great question. Let me make just one point clear. I mean, it's true. We have presented a particle physics perspective for dark matter, but this is not to say that this is all there is. There is so much more going on, and all of these alternatives are being investigated very thoroughly because, well, before we jump into very exotic possibilities, dark matter, dark energy, new type of particles, new slews of particles beyond the standard model of particle physics, you want to rule out everything else. So all of those other avenues have also been pursued and ruled out one by one. Now, I'm not an expert in terms of brain cosmology. My understanding is that those brain scenarios were brought in mostly to answer the problem of dark energy rather than dark matter and try to obtain an accelerating universe without the need of introducing dark energy. In any case, this is work that's being looked at, but the problem with that is that you also would have to explain, in terms of dark matter, effects which happen on very small scales, cosmologically relatively small scales, galactic scales, for which brains, which would only affect the universe as a whole, would hardly have any effect. And so the evidence for dark matter really spans a variety of scales, and a particle would be able to explain all of them in one go. So in a sense, although it's quite exoteric sounding, it is the simplest explanation. And not to forget the WIMP miracle, the fact that particle physicists can compute the amount of dark matter in cosmology from first principle, and out of the blue, you get the right answer without doing anything special. So the particle evidence is really compelling from a theoretical point of view.
Except that still no particles. I mean, lots of results of particles, but still no particles.
It takes a long time, right? It really takes a long time. The model we have for cosmology is incredibly simple. We take a photograph of the Big Bang 380,000 years after it happened, and then if you assume this model with dark energy and dark matter, you almost don't need anything else. You can then move forward and evolve that universe just with the assumption that there is dark energy pushing out and dark matter keeping it, sort of pushing it in, and you end up with a universe that looks like what we have now. So it's a very simple explanation that works from the smallest scales all the way to the largest scales. And also, you have the astrophysical scales. So our own galaxy has this dark matter. We see these effects in the way that bodies move in our own galaxy. So there are other explanations that people have proposed to explain different bits of evidence. The only explanation that hits all of the boxes in all of the evidence is this particle dark matter.
You mentioned that we haven't seen anything yet. Well, one of the particle physics theories is supersymmetry. So this explains that there's it makes a connection between the two distinct categories of particles. And in doing so, it proposes a whole host of new particles, one of which is light and is neutral and it's weakly interacting and is a perfect candidate for dark matter. And we're only just beginning to probe those scales. It's, we expected at the 1 TeV scale, and we're currently colliding at 13 TeV. And so we're just about probing those scales. So really, we're hoping in the next 5 years we will have closed in on some of these particles.
Did I understand you properly? The supersymmetry is already predicting something which is essentially a WIMP. That's what you're saying.
So that was a WIMP miracle, that particle physics, just completely independently, supersymmetry was proposed to explain very different problems, so problems with the Higgs mass, et cetera, But out of it pops this candidate, which is perfect. It has completely the right attributes to be dark matter. And that was why this connection between cosmology predicting the same particle with the same scale and particle physics completely independently predicting the same thing, this is what lends a lot of credibility to that, to the particle dark matter.
Right, you had a question here, yeah?
Yep. I think people should introduce themselves, so I'm interested to know where you're from. Questions?
Imperial graduate, 1963.
Hello?
Yep, that works.
Does it work?
Yes.
Doesn't seem to work. You sure?
You're doing well.
Okay, it's working. Yeah, I'm Piers Corbyn. I was an undergraduate here and graduated in '68. And we used to invite Professor Blackett here to little meetings on problems and paradoxes in physics when I was president of the Royal College of Science and Mathematical and Physical Society. Now, in those meetings, usually it was like, the question is it A or B? It's not A, therefore it's B. But, some of these arguments are like, it's not a dog, therefore it's a cat. So, the problems of a lot of the problems and paradoxes in physics are that there's other things which we haven't thought about or even known about, which pop up, as the last question asked. So I just want the speakers to address this issue. You see, when you talk about the WIMPs and so on, I'm completely stunned, and I think, wow, that's it. But then this guy pops up with, maybe not. You see, and when you talk about the galaxies, there's a lot of assumptions in there that the galaxies are in a virialized motion, and they're kind of orbits. Well, actually, maybe they're not. Maybe there's other reasons why things are moving like they are, and perhaps these galaxies are still expanding or something. I mean, see what I mean? There's assumptions which are not always listed. So I want to ask you, can you actually do without dark matter if you try very, very hard and think, no, could be this, could be that? Could you do without it? I mean, apart from the fact if we did without it, you wouldn't have any jobs, but leave that aside.
We would have.
Can we do without it? And is virialization, a dangerous assumption in galaxies?
Okay. People try to modify gravity, for example, on galactic scales to get rid of that matter, and it has been done initially on a very ad hoc scale, just as you suggested. Dark matter that seems to be preposterous. Let's do something else. Let's do something even more preposterous. Let's just change gravity. Einstein gravity is not only beautiful and theoretically compelling, it's also experimentally verified to very high precision, but only on scales which range from the millimeter to the solar system. So we're now extrapolating Einstein gravity to scales of hundreds and thousands of light years across and beyond. What is the evidence that Einstein works? Well, certainly the microwave background again provides such an evidence because that's based on Einstein gravity, but you may want to modify gravity ad hoc just to fit, for example, the rotational curves of galaxies without dark matter. And people have done so, and they even have come up with theories that can do that from not exactly first principles. At the beginning, they did it ad hoc, and that's always ugly in physics. You never want to do things ad hoc because everybody can fit something after the fact, right? So you want something that's theoretically motivated and that's the field. But the problem with this kind of modified gravity, or called variously called Mond, Teves theories, etc., those theories, they do not work. You can fine-tune them to explain the galactic motions, but then they fail miserably on supergalactic scales, they fail miserably in the solar system, they fail miserably with the cosmic microwave background. You can't fit all those observations with something that you've tuned to fix this problem, and then all the problems pop up all over the place. It doesn't work.
Hi. So you had, is it on? Yes. You showed a picture of the distribution of the WIMP, or the dark matter, and you showed that it wasn't spread out evenly, it was clumps.
It was lumpy, yes.
Why do they clump? Why don't they not spread out
That's
evenly?
what happens. So these simulations are very simple. You start with a very large number of point masses, uniformly distributed, and then you allow them to evolve under gravity, and then you allow that to merge with sort of other bits, other galaxies that you manufacture and so on. And what you find tends to be that you generate a lumpy distribution. It's a power spectrum distribution that there are a very small number of very large bumps and a very large number of very small bumps. Statistically, we are not likely to be in one of these enhanced regions, but that seems to be a feature of all of these simulations, that you develop this lumpiness. It's not a smooth distribution. That's something that 10 years ago we didn't quite know. So this is something that's reasonably new. So we thought this was a three-dimensional, beautifully three-dimensional halo of dark matter. That may be okay, it could have been a bit distorted, but it was nice and smooth. And now we know it's probably not smooth, but it's three-dimensional and it's very large, so that hasn't changed.
Do you want to comment on that?
Yeah, that kind of.
One of such simulations, it's that one.
Yes, I support peers. This is ultimately an experimental science, and if you discover something, that's wonderful, we've got the answer. I'm interested in what happens if we don't discover something. I mean, LZ is going to be 1,000 times more sensitive than LUX. Suppose you don't find anything. Can we imagine some super LZ? What I'm really getting to, can the theorists come back and say, oh, actually the cross-sections were smaller than we thought? Or is there some limit at which point you run into a paradox and you can say definitely it's not there?
We do it all the time.
Theorists are excellent and very bright people, and they have been doing this for a long time. So it's like the carrot, the experimentalist chasing the carrot. They can always come up with theories that predict more rare interactions than we are sensitive to. So that is something that will always happen because, I mean, we use predictions by theorists to motivate our experimental design, and then if we don't find it, then the theorists are motivated to find theories that predict even lower cross-sections, and then we chase that and so on. So that is something that happens, but in the end, we need to see something. If LZ does not see this, what happens? So we are approaching something that was in my plot, which seems to be a pretty fundamental limit to these searches, which is neutrinos are going to be a very serious background, an irreducible background for these searches. At some point, there is a type of neutrino interaction, which has never been seen, but we know is going to be there, that will start creating nuclear recoils like the ones we are looking for. And it seems pretty difficult to go significantly below that limit. That limit is just around the corner from LZ. What happens if we don't find it? It's possible that the true model is hiding below that limit. It's absolutely possible, and it's unclear if we can ever do anything about it. If we don't find it, we can also exclude a lot of other physics models that are trying to explain other things. For example, why is the Higgs mass the way it is, and so on. Where does the physics beyond the standard model? If we don't find anything with LZ, all of those models have to be discarded because they don't work. So this is all linked, and the fact that we can rule out physics models has implications for the rest of particle physics and vice versa. So we are learning by doing this, and even non-discovering. And non-discovery is something that moves us forward. Of course, we're not here to not discover. We really want to discover. But physics moves on even if we don't discover, because then we rule out. And we say, your Higgs model that you're proposing to explain why the mass of the Higgs is this does not work, because we would have found this dark matter associated with that model.
This theoretical and experimental search, as we saw, involves an awful lot of people, an awful lot of engineering, and an awful lot of money. So my question is, has anything so far come out of the work in developing the technology or the theory which has use outside of the search for the particle, for the dark matter particle?
we've been looking for supersymmetry since I was a student. So when I was a student at CERN in my first postdoc, 1990.
A few years ago.
1990. I was sitting in CERN, and around the corner was a guy working on some clunky program. And he said, "Oh, have a look at this." It was running on an IBM VM370 system. I don't know if you know those, or maybe some of you work with them. Good old-fashioned thing. And he said, "It's really great. It lets you look at your data at Stanford or over here at Fermilab, and you hit a 1, and it will show you the data at Fermilab, and you hit a 2 on your terminal, and it'll show you the data at Stanford." And I thought, wow, this is really clunky looking. But it turned out this guy was Tim Berners-Lee, and he was developing some tools for us to look at our data, which was being spread around. Now, that's turned into something that you probably use. And I pull that story out a lot because it's not often when you're doing really fundamental research that some tool comes out that's so ubiquitous that everybody knows about it. A lot of times we'll come up with tools that other scientists will use or other engineers will use or will push into medical technology. But sometimes when you're doing something that's so difficult to do, you have to push the technology so far that you end up doing something that affects everyone. And I wish I could predict that we did that every time we did an experiment like that, because we'd get funding much more easily. But sometimes you do. And the World Wide Web was a big win for this searches for new particles.
I'll give you a small example. The algorithm we used and that we developed in Zeppelin 3, the previous experiment, to reconstruct the vertex of the interaction, so you have an hexagonal array of photon detectors and you want to reconstruct the position of that interaction within a few millimeters, is now used in gamma cameras in nuclear medicine. Because it turns out that you can calibrate a gamma camera at the press of a button, and you do not need to pay for an engineer to be paid a huge amount of money to come and calibrate it and certify it every single 6 months or whatever. So it turns out the algorithms we use from particle tracking, optical tracking, and reconstruction methods are so advanced that the industry is actually catching on to this. And so we have many small stories like this, and the point is we can't predict. So the things that you can predict are the easy ones. So it's serendipities, and it turns out that some of the things you never thought were interesting, industry finds them interesting and moves them on.
If I can highlight another aspect of this briefly is that this is all now big data research. All of this is predicated on our ability to bring together, understand, and analyze very complex data sets which push the limits of what is possible to do computationally. In fact, some of those things have never been done before. That's why we do them. And the algorithms, the statistical methods that we develop, they blow out of the water anything that's available commercially, because those problems are so hard, so difficult, so computer time intensive, that we need to develop new solutions to even just make them possible. Moore's law is no longer enough. And so some of the algorithms for statistical searches of very complex parameter spaces are tailored to the searches of that matter, but can be lifted and applied in a completely different field. And we all know what big data mean these days.
So here? Yep.
In what sense is the WIMP described as, why is the WIMP described as non-luminous?
As? Non-luminous.
As non-luminous.
Because it does not interact with electromagnetic radiation. So with photons, it doesn't have a charge. So it doesn't have a charge. So we think it will interact via the weak force, which is a different type of force that is mediated by other particles, but it does not have electromagnetic interactions. It will never emit you directly photons, and it will never absorb photons, for example. So it's non-luminous in that sense.
Yes, here.
I wanted to ask what you thought about the recent observations earlier this year of ABLE, the cluster. Can you hear me? 3827, which indicates self-interacting dark matter and the possible existence of a dark force, dark photons, dark sectors.
It's flawed. There's been a reanalysis of those data showing that it's impossible. It made the news. Everybody talked about it, but the numbers they came up with, they've not been backed up by reanalysis by another team. It's over.
Hello. 2 points. One, just by the way, which was the justification for the research absent-mindedly spinning off useful things. You might say the Second World War span off lots of useful things, but it was incredibly expensive and hardly worth doing. So I don't think it's a real answer, in a way. But my second point would be, it's not clear to me exactly, with the experiments that are being carried out, when something impacts in there, that will be a piece of dark matter. That seems to be what you're saying. And if it is a piece of dark matter, what is it?
So if not everything that impacts on the experiment is a piece of dark matter, it has to be a nuclear recoil. So what I was showing you are probably, this is real data, so I don't know, but it's just normal election recoils. If we see a nuclear recoil, we can reconstruct the energy of that nuclear recoil. Yeah. And if we see 10, 20, 100, we can reconstruct an energy spectrum. And that energy spectrum is really important to tell us what is the mass of the particle that is colliding. So we get the mass of the particle, and we can also get the interaction cross-section, which is how many events we've got. And we can reconstruct the, if we run with a slightly different target, so for example, xenon has many isotopes. If we remove some isotopes from the mix and run again, we can probe the spin of the particle as well, because we can be sensitive to a particle with spin or a particle without spin, just changing the isotopic composition of the target. So we could, from these experiments, we could tell the mass of the particle, the interaction cross-section, and the spin, and then you put that together with the LHC information, and then you can probably recreate all the particle properties.
So that would then be the answer. That is what dark matter is.
It will give
or
you
is
the
that
answer.
just
This
a
is
bit
what,
of dark matter?
This is what the dark matter is in our galaxy. The question is what particle is it, and the LHC would be sort of the complementary part to this, to tell us exactly where the particle comes from, where does it decay, if it decays at all, and what produces it, and so on.
Yeah, you really need, so this is emphasizing that you really need an interdisciplinary approach here. So for instance, the collider, if we see a neutral, weakly interacting particle escaping our detector, we can say that, well, we've seen something new, something that's neutral, something that's weakly interacting, and hence probably has the right attributes for dark matter. But we will never be able to say that this is the cosmological dark matter, because we don't know whether it's stable. We only know that it was stable enough to have left our detector without interacting. We don't know they're stable on the galactic scales. So we really need corroboratory evidence from these other searches to really pin it down.
So like Roberto showed initially with this final set of plots, ideally the accelerators and the direct searches and the indirect searches will all converge into a spot in that plot. And if we do that, then we've pinned down the cosmological problem, the particle physics problem, and the astrophysical problem, and that is the solution. So that's the goal. Whether it will happen at the same time, I don't know, it's difficult to predict, but that is certainly the goal.
Can I briefly address your wider point about research absent-mindedly giving us something useful? Well, that's part of the reason why we do this kind of very fundamental research, but I also think that, first of all, we need to put this into context. The Large Hadron Collider might seem like an expensive toy for particle physicists to play with, but it's actually relatively cheap. It's only about the equivalent price of a coffee per European citizen per year. And what you get out of this is one of the most technologically advanced machine on Earth that's addressing some of the most fundamental questions about the very nature of reality. And that's really good value for money. Really, it is. And what all those questions do, they inspire a generation of students to come into physics, to do what you did. And for our first year undergraduate, they cite particle physics, cosmology, the big questions as the reasons for coming here and studying physics. And I think that's exactly what we need. We are a technologically advanced society. We need people like yourselves, graduates, people like that know what the value, understand the value of the physical sciences, and then they go off and do in society all sorts of things. Not everyone will become an academic. Otherwise, our jobs will be rather under pressure. But the point is that all the money that we invest in society in these fundamental questions, I think, is really good value for money. And it cannot all be quantified in terms of 5 years plans, 5 years horizons, but it's really high return for the investment.
Thank you. One here.
Right at the back there.
Thank you. I had a question for Dr. Malik, but first I wanted to assure you that although I have had affiliation with Atlas, I'm not the wrong experiment. I don't ask as an Atlas spy, but rather as an Imperial alumni. When you mention looking for signatures in the CMS experiment, Large Hadron Collider, it's going to be similar to missing mass and therefore neutrino. How will you actually, are there modifications to the detector to rule out that it's always a neutrino? There's a certain ambiguity which will be left.
It's actually incredibly difficult for us to discriminate whether a collision has produced neutrino or a dark matter particle. It's extremely difficult to discriminate those. And this is where our theoretical understanding comes in. So theory predicts that we should see this many neutrino events. And so we rely on the fact that if we see any more than that, our theoretical predictions are very accurate for what we expect, for how many neutrino events we expect. And so if we see any more than that, then we know that we've discovered something, or we've seen an excess of something that doesn't tally with our theoretical understanding. And so, detector-wise, or in terms of what we see as a particle, it's going to be very difficult for us to discriminate between a dark matter particle and a neutrino.
Thank you.
One way at the back there.
I just want to ask you about the advantage of studying WIMPs compared to other dark matter candidates. For example, the axions, people are studying other kinds of...
That's a very good question. So axions are also a well-motivated dark matter candidate. And there's dozens of others, but the dozens of others tend to come and go very quickly. So over the years, I've counted like 100 candidates. Most of them live for 1 or 2 years before somebody finds a flaw in the theory of it. I couldn't hear that. That will be the giveaway, that's right. And so most candidates come and go. Axions have stubbornly been there alongside WIMPs. WIMPs are slightly more favored, but axions are also a worthwhile experimental endeavor, and people are looking for axions too. In fact, even in these kinds of experiments, we are sensitive to several axion models, and we do look for axion interactions, not with the nuclei, but with the electrons as well, because axions are a well-motivated dark matter particle too.
Thank you.
And the astrophysics kind of works too.
Mine combines several answers which you've already given. One relating to obviously whether it's a neutrino or or a particle of dark matter. But my concern is really on the theoretical side. If you have 4% matter, and we do not know, and there is no valid explanation as to why it is all matter and very little antimatter in the universe, you have WIMPs, WISPs, whatever you want to call them. These particles are dark matter. Where is the anti-dark matter? Are they their own anti-dark matter?
That's a very good question. And there are models for dark matter that attempt to address that there is an imbalance between matter and antimatter related to this CP violation problem. And it is possible that the same problem exists in the dark sector. And there is a kind of model called asymmetric dark matter that is plotted as one of the regions in my plot that we are also sensitive to, and we are also cutting into that model that actually explores that kind of possibility, that the same problem that exists in ordinary matter exists in the dark sector too, and the two are linked via some particle that mediates between the two worlds, and it really attempts to address that problem, which is why is the amount of dark matter, which is a mystery, the amount of dark matter is comparable to the amount of matter, factors of 5. That's not a lot. The way dark matter is produced, we are proposing, is fundamentally different to the way normal matter is produced. And yet we end up with the same number of billions within a factor of 5. And that suggests that there may be some link between this asymmetry, matter-antimatter asymmetry, in the dark sector and in the normal sector.
Could it also be that dark matter particles are in fact their own antimatter particles?
So WIMPs, yes, WIMPs are their own antiparticle, yeah. But there's a different kind of theories that propose asymmetries as well.
Right. So I think we do have drinks waiting for you, but I want to. Well, you know what? I think we can do that over a drink, because what's going to happen is I'm going to say a few words to you, and then we're going to work to get you upstairs to level 8, where the drinks are, and Tom will also finish off and send you upstairs. So first thing I'd like to do is to thank the 3 speakers who I think did an outstanding job today. So they're going to be upstairs, and you can corner them and ask them all the questions you like that maybe you didn't want to ask in this forum, and they'll do their best to give you some sort of answer if they can. I wanted to just say a few words to you about why we're doing these events, because I think it's important, and I think a few questions came up that illustrate that. So about 3 weeks ago, I had the first-year undergraduates sitting in here, and when they come in, they're all a bit nervous, and I'm their first greeting to them, and I welcome them, tell them how well they've done to get in, and then I remind them something that I remind my own children, remind myself, that when you go to university, this is where you really create your strong network of social and professional connections that can last through a good part of your life. And I think that this institution is part of the lives of our young graduates, and I think many of you are, as alums of this institution, also part of their network, and we're part of your network. So I think it's our duty to keep you involved in what's going on here, as well as to just keep pushing students through every year and keep you in contact with them as well. Just a little framework for you about how student life has changed. So, some of you, those of you who graduated in 62 or 63, probably had a very different experience as a student than the students are having today. The students are paying tuition, for one, which is different, and that's just a change in the landscape. And it's something we as an institution are now quite dependent on in terms of how we operate. And on the other hand, we're competing to get the best students in the world in here now. So we, in the physics department, our job is to attract the best researchers, the best students in the world. And we actually can do that as a top institution in the world. London makes that challenging. It's not the, central London is not the easiest place to build new buildings or to house people, but it's still, this institution is really attracting the best people. And you've seen the type of research that's going on here. So, Henrique built bits of Zeppelin upstairs, right? That's one of the really groundbreaking experiments. The bits of the CMS detector, the heart of it, some of the electronics of the real heart of the detector were all designed and built upstairs in this building. So real things are going on in here which have taken real investment. Now, who does the investment? For the most part, the government does the investment. And as you say, it's not something, it's pure research attracts less industrial funding than government funding. But that means our researchers spend an awful lot of time trying to get the message across about how exciting the research is and how valuable it is to be funded. And I think your question was quite a good one. It's quite an important one, and I'll come back to it in a second, how I might answer that as well. I think Roberto did a great job of answering it. But it's really, I think what we want to do is to keep you involved in helping to spread the message about why it's good to invest in science. We want you to be part of our message to the community, to your professional circles, to people you know about why it's good to invest in science. And we want you to understand what we're doing and the excitement, why we're still doing physics in this building 60 years after it was built, and really enthusiastically about it. So part of the reason we're trying to have these events, and we'll have them more often, is to get you, our graduates, and the members of the community to be kind of, if you like, promoters of science in the community. And I think that's a really important thing. Champions, if you want, I think is the word that they'd like me to use, but I think it's a good word. So let me just answer the question, because I was going to answer. I was going to answer that question anyway as to why are we doing things like studying the Higgs boson? And I get asked this, actually, the taxi drivers almost never ask me that. They say, it's so cool that you're working at CERN. I really enjoyed that. That's great. Worth every penny. That's really honestly. Politicians are the most skeptical, and they'll come up to you and say, so why should we be funding you? With the same sort of skepticism, it's, okay, it's exciting, whatever. And I think I can give the answer already I gave about spin-off technologies. For sure, I cannot predict what we're going to use a Higgs boson for, right? I'm not going to tell you there's going to be flying Higgs boson-powered cars just 10 years down the road, right? But there may be something in 100, 1,000 years where we use the actual discoveries in something in our everyday life. I can't predict that, right? It's just too far out. And that's also was true of things like quantum mechanics. How would that be useful? Well, now it's used every day in all sorts of things. But when you're doing groundbreaking research, it sometimes takes hundreds of years to get something out of it. The technology spin out, that's another thing. I gave you the World Wide Web example, and it's a real thing that you can see. Again, it's some serendipity. You don't always predict exactly what's going to come out, but I'm for sure there's going to be a steady stream of useful technologies coming out when you're pushing the limits of human knowledge in this extreme a way. But I can't tell you where it's going to be. It just happens. The one thing I can predict with absolute certainty is a complete flood of really well-trained graduates coming out of this place. And that's what I tell the politicians is the impact that I can guarantee is that when the students that we bring into this place, the researchers that we bring into this place and train solving these problems, go out and do an incredible array of different things. And that is an impact on society that you cannot overstate. It is really important, and it's a really important mission that we have, is to provide some place that's enthusing young people to learn how to challenge, to solve really challenging and incredibly difficult problems, and then go out in the world and find problems to solve. So that's the impact, I hope, that I can sell to government. And if you want to be our champions, and when you're at cocktail parties with the chancellor, never hurts to drop a good word in for physics, please do. So thank you once again for joining us today. I'm going to turn over to Tom, who's going to lead us up to drinks.
Thank you very much, Jordan, and thank you, of course, to our three speakers for being so impressive. But I should say we've just been commenting down in the corner where I am. We expected the three speakers to be impressive. When I meet young academics now across the whole of science at Imperial, I came from the chemistry department, I'll talk about that in a second. As I meet more and more people from across the whole of science at Imperial College, I'm always impressed. It was absolutely my expectation. What was not my expectation was how well informed the audience was going to be. And so well done to you. I think it was really impressive. Yes.